All right, here we go, Unit 6, Lesson 4. Today we're going to be going over the fundamental theorem of calculus. And as you can probably tell by its name, it's the single most important theorem that we're going to learn in calculus. It's what links the first half of the course, which is all about derivatives, to the second half of the course, which is all about integration. And the fundamental theorem of calculus shows us that these two items are actually intricately linked through the concept of area under the curve. I'm going to divide this video into two portions, one that goes over a proof of the fundamental theorem and the other that goes over using it in practice. On the AP exam, you are never going to have to prove the fundamental theorem of calculus, but it is accessible at your current level of mathematical sophistication, so I do want to present it. Watch it once, get a feel for it, but don't stress too much if this goes over your heads a little bit. What's important is being able to apply the fundamental theorem later, but it's worth seeing once. So here we go. I want you to imagine we've got this function here, the blue line y equals f of x. And I've shaded under that blue line an area in blue that we're going to call capital A of x, which I'll explain in a second, and a smaller area shaded in red. And so the first really important thing is that I've defined this function a of x so that a of x, and I'm going to write this down because it's so important to really see what's going on here, a of x is the area under f of x, so under that blue line, the area under f of x from 0 to x. So whatever you plug into that function, it tells you the area under the curve from 0 to x. We're making it up right now. It's purely theoretical. But let's say we wanted to use that function to find the area of that red shaded region. Well, one thing I could do, that area would be perfectly defined if I said first find the area of x plus h, right? That's this point right here, so the area from 0 to x plus h under the curve, and I subtract the area under the curve from 0 to x, right? So if I were to take this whole area all the way and then subtract just the blue part, right, that would tell us what the red part is. Now we can also think about that area geometrically using f of x. We know that the length of this rectangle from x to x plus h, well, that's just h. And the height of this rectangle, right, which is almost all, but not all of it, well, the height is going to be f of x, right? This point right here is the point x comma f of x. So f of x tells us the height. So if you did h times f of x, you'd have that rectangle. Now, obviously, it's not a perfect rectangle. There's that missing portion, which I'm literally just going to call right now plus the excess. So plus some little extra area. And this is an equality here. These two things are exactly equal to each other. And one thing I could do is I could rearrange this equation. I'm going to move the excess over to the left-hand side. So I'm going to have a of x plus h minus a of x minus that excess. And all of that is still going to be equal to h times f of x. So I'm going to do another trick here. I'm going to divide through. I'm going to divide through by that h. And what we would wind up with here, right, what we would wind up with is, on our next line, a of x plus h minus a of x all over h. I'm just splitting this up a little bit, minus that excess piece over h is equal to f of x. Now, it turns out that if you take the limit as h approaches 0 of both of these sides, if you take the limit as h approaches 0 of both of these sides, as you get smaller and smaller and smaller, this portion right here heads to 0, it turns out. And so when you take this limit, right, and that part is also accessible, but it takes like another page to prove it. It's just not worth it given our time restrictions right here. But you get the idea. As you take a smaller and smaller and smaller red slice, this little part right here, you can just say that little part right there is going to head to 0. And so what we're left with, right, is that the limit as h approaches 0, and this is all going to click in just about 10 seconds here, minus the area from 0 to x over h is equal to exactly f of x. And so what's the trick here? The trick here is that this, you'll remember, is the limit definition of a derivative. It's change in y over change in x as the change in x approaches 0. So this right here is literally the derivative of that area function. The derivative of the area function is equal to the original function. That should be like a super important, mind-blowing conclusion, right? That is at the heart of the fundamental theorem of calculus, is that if I have a function that defines the area under a curve, I made it up, but if I knew what it was, if I could take its derivative, I would have the original function. And so what we have here are sort of two super important, mind-blowing conclusions. That the derivative of an area function is equal to the original function. What that also means is if I take the definite integral, or if I take the integral of the original function with respect to x, I will have that area function plus some c, right? And so this right here is the first really important part of the fundamental theorem of calculus, just the relationship there between a derivative and an integral. And we've already worked with those definite integrals, right? We already know a little bit about these area functions from Riemann sums, right? We already learned that, for example, like the integral from 0 to 5, or 1 to 5, the definite integral from 1 to 5 of f of x represents the area under the curve of f of x. So we already have seen that, and now we're seeing how those two pieces come together. So here's the actual fundamental theorem of calculus. Let's say if I wanted to find some intermediate area, like the area from A to B. Well, one trick that I could do, right, what I'm looking to do is I'm looking to take the area from 0 to B and subtract the area from 0 to A. Now, if I don't have that area function, the trick here is that I can take the antiderivative of the original function evaluated at B, so take the antiderivative evaluated at B, and subtract the antiderivative of the original function evaluated at A. And as we've already seen before, we have a special symbol for this. We combine this into a single definite integral, the definite integral from A to B of f of x is how we would represent that. And so here is the fundamental theorem of calculus. This is equal to, we learned up here, the antiderivative of the original function is the area function. And so this is equal to the area of B minus the area of A. Now conventionally, right, instead of using that area function, we're going to say instead the way we represent an antiderivative of an original function is a capital F. So we're going to call that capital F of B minus capital F of A. If I was reading it out loud, I'm going to read this entire portion out loud, and then we're going to just close with an actual, like, here is again the fundamental theorem of calculus. What this says, I'm going to cross off this another A right here so you can see it. The definite integral of f of x from A to B is equal to the antiderivative of f at B minus the antiderivative of f at A. That capital F right there, that is a shorthand for saying the antiderivative of f of x, and you can evaluate it at a specific number. And so here we go. This is just so you can have it all in one line in computer type. Everything I've done so far, hopefully like you're like, okay, like maybe you didn't like follow exactly every portion of it, but the ideas are there. This is the part that you actually need to have memorized. If f of x is a continuous and differentiable function, so it's a normal smooth function, no weird jumps, this part right here is one of the single most important. This is up there. This is up there with the derivative is the slope of the tangent line. The definite integral of f of x from a to b is equal to the antiderivative of f at b minus the antiderivative of f at a. That's a mouthful. You could also say capital F of b minus capital F of a when you're just communicating this really quickly. And so that's the fundamental theorem of calculus. I'm going to break this up, so we're going to have another video here just so you can really like watch this one once. No need to watch it again. The next one's going to go over a lot of the practical how you would apply the fundamental theorem of calculus.